Uh, uh, uh. Okay, in the chat, can you see the slides?
Yep.
Thank you. Okay, so a couple of things. I started grading your exams. I think I'm done with the first section. For the second section, I think half your exams already graded. I will finish the second half today in the next couple hours after the class. When you receive your grade, I couldn't make any notes on your PDF file or anything. I tried to make a small comments, things that I saw, like, oh, you made a mistake on the sign, or you made a mistake on the equations, or sometimes it's like, okay, we need to talk and we need to figure out exactly what is the error. Once you see that those corrections, then if you want to see your exam, we want to review your exam, we can sit down and review it. And if you want to redo the exam, you can do it, but I want to make sure that you understand where your mistake, and that if there's a misconception, that you understand the concept correctly. The last thing that I want is to give you 2 chances, 3 chances, whatever, to redo the exam, but if we don't review it, then you're gonna be making the same mistakes over and over, and it's not gonna help you. There's no a deadline for you to do the second chance of the exam. If it takes you a week to have everything ready and you want to give it a try, it's going to be a week. If you can think that you can do it tomorrow, will be tomorrow. If you need a month to get ready, that's fine. I really don't care if it's. I care that you can understand the material. Whether you understand the material today or you understand the material in a month makes no difference. So I just want to make sure that you understand and that you can pass the exam. So just wait until today at night, and you should be able to get your grade, or you already have your grade. This third homework, I will start grading it tomorrow. I will imagine that you guys are more interested in the grade of your exam than the grade of the homework. So I'll put the grade on the exam of the grade later this week. This week, we're still going to be working on chapter 8. Just one topic. We're going to cover most of it today, and then we'll do problems on Wednesday. And Friday, we start with chapter 9. There's no quiz for chapter 9. I'm going to do the same thing. I'm going to give you a quiz sometime in the middle. And I will put the homework on Friday to do next Friday. Make sense? Okay. I usually don't do slides. I don't like the slides. But I have this one ready, so I might as well use it. For some time, so in the morning it was very tough. This class, like everybody was falling asleep because slides, like 8:30, and my voice is kind of like same tone. So yeah, they was falling asleep. So if you fall asleep, that's fine. I'm not gonna get offended. I understand completely. In the chat, yeah, same thing. Don't worry. It is what it is. So these are lectures from biomechanics. I used to teach that biomechanics class. And this is one of the topics that I wanted to bring back to this class. I'm not sure if Dr. Hoffman is talking about this on her biomechanics class currently. I think she's not, but it's kind of interesting. So I thought it would be kind of cool to do it. So, so basically what we're going to be talking about is, we talk about how forces can move an object from one place to another. And then we talk about how forces can rotate an object. And then the last thing they want to know is, okay, how forces deform an object. So this second part, or this last part, is to talk about that, about the deformation of object caused by forces. Specifically, I'm going to be talking about the bones, just because that's the one that is more accessible for the math and the concept that we've been talking. You can talk about the formation of muscles and arteries and your lungs and your skin, but those models tend to be a little more complicated. Bones, they're just not complicated. Well, not as much complicated. Okay. Okay. So one of the things, instead of talking about forces, in biomechanics, you usually talk about loads, but it's the equivalent. It's the same idea. A load is just a force that's being applied to an object. And what we want to know is how those loads affect that object. By the way, I'm pretty sure I uploaded these slides already on Canvas. So if you go to that module of torque and elasticity on the topics, you should see the PDF file with the slides. If they're not there, just remind me. So what we've been talking about so far is an area of physics that's called mechanics. And within mechanics, we have the mechanics of rigid bodies. That's what we talk. So objects that they don't deform, that they can only rotate or translate. We can also have the physics and the mechanics of deformable objects. And again, this can be very simplified or very, very complex. If you have, the skin is extremely complex just because it reacts differently of how we apply the forces. There are some materials that we think to be very rigid, like concrete. But if you have that concrete under a lot of vibrations, they become flexible. If you imagine the roads in Michigan, you have concrete on the streets, but after a couple of months of just having trucks over and over and over and over, that concrete breaks, and it's just because of these tiny vibrations. And you have objects like the bones that they have a range of loads that they are exposed, and they are, depending on the shape and the function of the bones, they support some loads better than others. So even though the material of the bones on your ears is the same as the material of the bones of your skull or the bones on your femur, just the shape and the function makes them behave completely different. So the bones on your ears are not as strong as the bones on your head, or the bones on your rib cage. They are designed specifically to support a specific kind of load that the bones on your femur are not designed to do. So that's some of the things that we're going to try to do. And fluid mechanics is the last part of the area of mechanics. I hope that we can talk about this later in the semester. All the years I've been teaching this class, I never have enough time to cover fluids. Fluids is pretty interesting just to talk about how the blood transfers in the body and how your lungs work. It's just kind of interesting, and how your body reacts when it's under different kind of pressures. So hopefully we can do that later in the semester. So rigid mechanics is the one that we've been talking so far. You make simplifications of the object, and you sometimes do a lot of simplification. Sometimes, basically, what you are simulating is not very realistic to the thing that you are doing the experiments on. So, for example, if you are doing an experiment on clay, and you look at the forces being applied for clay, you may be able to predict motion and how it's going to translate or rotate, but you don't do anything about the deformation of the object. So we do a lot of simplifications. We use free body diagrams, but we don't care about bending or stretching or compressing or anything like that. So we just stay with rotation and translations. Sometimes we even ignore drag, friction, and so on. Okay. If I'm going too fast, just let me know. Send in the chat. If I'm going too fast, just let me know. Now, one of the key concepts that we need to understand to talk about deformations is the idea of pressure. Pressure is what we're going to be using to when we talk about the deformation of objects. So it's not only the force that we apply that deform the object, but it's the area in which that force is being applied. So if you imagine someone slapping someone, Mary, have you slapped someone?
Yeah.
I just say with that pride, like, yeah. Did he deserve it?
Who says it? Why would it be a he?
Well, he or she deserve it?
Yeah.
Oh. That's tough. Okay, so when you slap someone, well, you slap it with your open hand, and you can imagine that the shape of your hand, the force is being distributed along that area of your hand. But when you punch someone, have you punched someone?
Not on purpose.
But you have.
Yeah.
The same person?
No.
Oh, that would have been more fun. But when you punch someone, then the area of your fist is much smaller than the area of your hand. So even if you apply the same force, it's going to hurt more just because the pressure is going to increase. That's if you have seen those magic tricks that you have a person laying down on a bed of nails or walking on glass, is basically that idea. You have the weight of the person, but it's distributed in a big area. So the pressure on each individual nail is not as much as if someone is walking on one single nail. The units for pressure are pascals, and the way we define a pascal is just a Newton divided by square meters. So when you're working with pressures, make sure that you are converting everything to meters and everything to newtons. If you work with newtons and centimeters and you divide and stuff like that, you're not really doing pascals, you're doing something else. Okay, so just make sure that you have these units correct. Another unit that is very common and still very common in industry, is very common in some areas, is pounds per square inch. Is one of the few areas, pressure is one of the few areas in which the English system still is being used, even in countries that don't use the English system for some reason. It's just because of engineering and the machines that are being designed. They have the specifications in pounds per square inch or PSI. So kind of fun, kind of weird. So a very classic example of looking at the difference between, to distinguish between pressure and force. So imagine that you have an elephant, and an elephant weighs 3,000 kilograms. And when it walks, it's distributed its weight in 2 feet. And you can assume that each feet, or each foot has an area of 0.026 square meters. So if you calculate the pressure, so you divide half the weight, because you can assume that the weight is distributed in the 2 feet. So if you have half the weight to do in that area, so 1500 times 9.8 divided by 0.026, you have a pressure of 565 kilopascals. Now, if you look at the pressure of a person walking on heels, I'm not going to put woman there, but now I have to correct it. If a woman walking on heels, and you assume that that woman has a 50 kilogram mass, so the weight of that woman will be 50 times 9.8, and then divided by the square inch of one heel, which we have 6 square centimeters. So that's you end with a pressure of 816 kilopascals. So the pressure that the woman has on the bottom of the heel is bigger than the pressure of the elephant on the bottom of its feet. So this is just an idea to get you to understand what is the difference between pressure and force. So just because something is very massive, doesn't imply that it's going to have a lot of weight. It's going to depend on where is the area and you apply that force. Okay. So you can imagine when you are jumping, you have all that weight on your bones. The bones that are narrower or that have a smaller cross section are going to have a higher pressure than bones that tend to be bigger. Okay. Now we're going to be talking about the strength of materials, specifically about bones, and there are going to be some numbers talking about the different forces and strength of these materials. But one thing that you need to understand is that as we grow older, the force or the strength of our bones is going to change. As I mentioned before, the function of the bones also are going to define the strength. So it's completely different. The bones on your skull, that they are protecting a vital area of your body, that the bones on your toes or the bones on your ear. The strength is different. The shape is going to affect. The age of the patient is going to change. And also, bones react different depending on how we apply the forces. So if you are compressing a bone, or you are stretching the bone, or you are bending or squeezing the bone, they react different. So the numbers that we're going to see, just take it with a grain of salt. There are standards, and also many of the tests that we have to measure the strength of bones are destructive tests. So there's not an easy way to measure these bones in live patients. You basically need to work with cadavers. So there's always kind of weird of how you test these numbers, okay? So these are the main forces that we're going to be talking. These are the main loads that we're going to be talking on bones. We have compression, that is compressing an object. Compression is usually along the long axis. So if you have a structure that looks like a tube, there's along the long axis. That's what we have. That's what we talk about compression. Tension will be the opposite. So compression, you have two forces facing each other on the ends of a bone. Tension, you have two forces, but now they're moving in opposite directions along a bone. You have shear. Shear is kind of weird, but especially all athletes, football players, lacrosse players, basketball, soccer, the main injury that you have in your bones when you break the bones is caused by shear. When you tackle, or when you have two forces in opposite direction and they're in lateral way, your bones tend kind of to cut, or that's shear. And it's a cause of the most common cuts. Fractures in the bone. Torsion, you have two bones. You have two forces. One is clockwise, the other one is counterclockwise, in opposite direction. Well, clockwise and counterclockwise, and they're basically twisting your bone. Now, there are forces that are a combination of these 3-4 basic loads, or there are consequences of not applying these loads in the ideal way. So bending can be seen as you have a compression force, so you will have a force on the top, a force on the bottom, and then you may have a lateral force, and that causes the bone to bend. You can also have compression forces, but instead of being perfectly on the axis, if you have a force that is off axis, it can cause that bending. So we have more complex forces There can be a combination of these four basic ones, okay? If you have a questions or anything, just let me know. Now, before I continue, how many of you have taken physiology, anatomy? Okay, so if I say something stupid, just let me know. Just do it nicely, just very politely, like, I think that's not what you think it is. Okay, so when you apply a compression force, the object is going to deform. When you compress, what you usually see is a bulging on the object. The bulging is usually at the midpoint of the object, but that's not necessarily is going to be all the time. What is interesting to see is that this bulging is proportional to the amount of force that you apply. You know? No? Okay. So if you apply 10 newtons, you're going to have some deformation. If you have 20 newtons, you're going to have a deformation that is going to be larger than what you have at 10. And when you have a 50, it's going to be larger than the previous two. Doesn't mean there's going to be twice as the one on 10 newtons, or there's going to be 5 times as much as the one on 10 newtons, just that it's going to be larger. And we're going to see if there's any relationship between those deformations. Okay? So again, the way we define compression is that the forces are applied on the long axis. If you have forces applied on the short axis, it's not really compression. It's more like a squeeze. But the compression is specifically on the long axis. There are some bones that they don't necessarily have a long axis, like the skulls, like the flat bones on like the bones on your skull. But here in this specific case, we're talking about just on the long axis, long bones like the bones on your extremities. Now, besides that bulging, sometimes what happens is that the object may bend. And again, the bending may occur because the forces are not exactly on the axis, on the long axis, or maybe because besides that compression force, you have an additional force. But when you have bending is a complex deformation because you have two forces, you have two different kind of loads in the same object. So when you're bending an object, when you're bending a bone, the inside is going to be under compression and the outside is going to be under tension. And that is going to affect how your bones break. We're going to see later that basically a bone has a very high strength when it's being compressed, but it has a very low, or it has lower strength when being stretched. So if you have something that is bending, eventually it's going to break, and it's going to break first in the area that is in tension, or is it going to be breaking in the part that is under tension, and this under compression is not going to break that much. So you can see where the trauma occur if you see one of these fractures, just because of where the bone is break. Tension is the opposite of compression. You are stretching the material, you're stretching the bone. We assume that you're stretching on the long axis of the bone. The same way that with, well, not the same way, but when we compress, we have this bulge somewhere in the middle. When we stretch, we have the opposite. There appears kind of like a neck. And that neck, if you keep stretching the object, you imagine that you're stretching, eventually it's going to come to it's going to break. And when you're stretching materials, they're always going to break on that neck. So that's going to be like the weak point. So as you stretch, the material is becoming weaker and weaker and weaker, and that weak point is the neck of that's why it's called the neck. You don't see that on bones that much. You see that a lot in metals, or if you have some plastic that is melting, And you imagine that plastic melting that's falling down, and it's gonna create like a blob, and it stretches, and then there's gonna be a neck, and that's where it breaks. And here again, it's this lateral motion that you have on a bone. It happens a lot, for example, football players that they are, or soccer players that you have the cleats on the ground. You try to cut, you try to cut a player, and then you move into one direction, and then you receive the hit in the opposite direction. You can imagine that your feet are trying to stay still, or trying to stay fixed in the ground. You receive a force in the other direction, and then your bones break. Is the most common kind of injury that you have in sports is because of shear muscles. Also, well, ACL ruptures are kind of weird because that's a more like a rotational motion that your body's rotating too much. But shear is very common on football players. Okay, so again, same idea on the tension compression can be applied to shear. You have a force, and the force is going to deform the object, and the higher the force, the higher the deformation is going to be. Okay, so there's a proportionality constant between the deformation and the force that's being applied. Still awake? Hanging in there. In the chat, that you guys still hanging in there? I think they're gone. It's just like Elizabeth. You still with us? Sylvia? Yep. Okay. And this is not even a third. Okay. So we need to find a way to talk about or quantify these deformations, and we need to quantify this pressure, and we need to find this proportionality constant that tell us how much is going to deform depending on the amount of force. Now, we borrowed these terms from engineering and physics, and basically there are going to be three terms that are basic to understand. One is what we call stress, strain, and the Young modulus. Stress is just a different way to talk about pressure. Okay, pressure, but the way we talk about in physics is something that is compressing. In engineering, we talk about stress is just a force that's been applied on an object. So it can be compressed, shear, or tension, but it's the same definition. It's just a force applied on a given unit area. It has the same units of pascals or newtons per meter square, but the definition is pretty much the same. We use sigma or tau. For the class here, I'm going to use in sigma, just to not confuse with the torque that we just covered. The strain, we use the letter epsilon, and strain is just the percentage of the deformation. So if you have an object that is 50 centimeters, and after applying force, it deforms 1 centimeter, then you can calculate that ratio and that percentage, and that's going to be the strain. Okay, this is an adimensional quantity. It's a percentage, so it's adimensional. And Young modulus is that proportionality constant. Is the one that's going to connect the strain with the stress. So if we apply a force, how much is going to deform is going to depend on this Young modulus. The higher the Young modulus, the stiffer the material. So a piece of clay is going to have a very low Young modulus. A piece of steel is going to have a really, really high Young modulus. Okay? Yeah, makes sense? Any questions? Okay, so before we go on, we're going to look some examples. Before we go through this, I want to show you a graph of stress and strain. I think here I have the axis wrong. I think this one should be stress, the one on the x-axis, and strain should be in the y-axis. But I'll double check that. So basically this graph, what tells you is, okay, you apply a force and that object is gonna deform, and you're gonna figure out, or you can try to figure out how much is gonna deform looking at this graph. These graphs are very important. Each material is gonna have a different kind of graph. So if you're talking about bones, and you talk about the different elements of the bones, so if you have the cortical bone or you have the trabecular bone, each one of them is going to have a different graph. If you're talking about steel, you're talking about plastic, each one of them is going to have a different graph. And there are three areas that we care. We have the elastic region, this one in black. We have the plastic or non-elastic region, that is the one in red. And we have the fracture area, which is just at the end. Okay, so elastic region, so you have a material and you apply a force or you apply a stress, and that object is going to deform. The deformation is not permanent. If you remove the force, the object goes back to its natural position or to its original shape. So if you have your bone and you are jumping and you have your bone under stress, your bone doesn't become permanently deformed. As soon as you stop jumping, your bone goes back to its natural position. If you have a ruler made out of wood and I bend it, you can see that it's being bent, but at the moment that I release the strength, it goes back to being straight. So that's what we call as elastic material. Elastic material is something that it can be deformed, but once you remove the stress, it goes back to its shape, like an elastic band. You imagine a rubber band, you stretch that thing, you remove the strength, and it goes back to its natural shape. So that's this elastic region. The elastic region is always going to be linear. It's always going to have this linear shape. And the slope of this linear area, that's the Young modulus. The value of that slope is the Young modulus. Okay? I didn't put it there, but I wrote it down. So the slope of that region, of that linear region, of the elastic region, that's the Young modulus. If you keep stretching the material, there's going to reach a point in which the deformation that it has is going to be permanent. That point, when you go from an elastic from a non-permanent deformation to a permanent deformation, that's called the yield point. So you go from the elastic region, where the deformation are not permanent, and then you go to the non-elastic or to the plastic region where the deformation are permanent. So anything that happens to the object after this point is going to stay like that. Metals have a very classic plastic region. So you have a piece of metal. You can be playing with a can and you can kind of squeeze it and it goes back to natural shape, and then you squeeze it too much and then it becomes permanently deformed. So metals have very clear separation or division between the plastic region and the elastic region. And then if you keep stretching that material, just keep applying a force, then the object is going to break. And that is basically this failure point. Okay, and it's basically the moment in which the object breaks. Different materials, they're going to have different, let me say it again, not all objects are going to have, not all materials have a clear elastic plastic and failure point. Some of them may have a very short elastic area. Some of them may have a very long plastic area. Some of them may have are very brittle, so they just break really fast, like chalk. Or some of them may not even have a breaking point. So, for example, if you think about Play-Doh, you guys play with Play-Doh? Mary, do you play with Play-Doh?
Not currently, but I used to.
Not currently?
No,
Why not?
I don't have any.
I can bring you one. Yes. You have Play-Doh?
Yeah.
Awesome. Why you have Play-Doh?
I have little things that I like to play with in the middle of class.
Do you have, it's not Play-Doh, what do you call it? Silly Putty?
No.
Ah.
This is some other thing.
Okay, that's awesome. Thank you. Okay, I'm gonna switch. Where's my mouse? There it goes. Okay, can you see me in the chat? Can you see the little Play-Doh? Okay, so a Play-Doh is a material that has pretty much doesn't have an elastic region. Elizabeth, you cannot see the Play-Doh you sleeping in class.
I would like pictures.
Do you imagine it? Okay, so a piece of Play-Doh clay, these are materials that basically they don't have an elastic material or elastic region, meaning that at the moment that I apply a force, or the moment that I stretch it, it becomes permanently deformed. And it's gonna stay there until I apply more force. And basically they're just gonna stay there, okay? So this is an example of a material that basically, if you were to see this graph, it will have pretty much a almost non-elastic region, and everything will be a plastic region. And you can see that as I stretch, there's going to be a moment in which it breaks, and that's going to be the failure point. Okay. This piece of plastic over here, I can bend it a lot, and then it goes back to its natural shape. So this one has a very long elastic region, and pretty much it doesn't have any plastic region. If I keep bending, it's going to break, but there's never going to be a point in which it's going to stay just bending. Okay, so this is an example in which a material that has a very large elastic region, but very, very small plastic region. Oh, thank you for your, let me play with your Play-Doh. I have Play-Doh. Also have two little kids, and then we play so. Okay, makes sense. The bones, or if you think about the bones in your extremities, they have an elastic region, but we don't have a plastic region. Hopefully, I mean, and that's actually a good thing. It's not like you bend your bones and then your bones become permanently deformed. You bend the bone and then you pass a threshold, the bone breaks and you have a fracture, but it's never going to remain deformed after applying a force. I'm going to go back to the slides. Okay, so again, the Young modulus is the slope of this elastic region, and it just tells you how stiff a material is. The higher the Young modulus, the stiffer the material is. So clay is going to have a very low Young modulus, still has a really, really high Young modulus. Well, never mind. Okay. So how do we measure these deformations? So how do we measure? How do we come up with these graphs? There are different kind of machines. This is usually used in mechanics and in mechanical engineering. These tests tend to be destructive. So whatever you're going to be doing, you're going to be testing until it breaks. So you can have a small wire, a small piece of metal, and this thing is going to stretch, and they're going to measure the force that's been applied and the deformation that you have, and it's going to be stretching this thing until it breaks. You have what is called a 3-point test, that basically these are going to be moving against each other. It's going to bend the object until it breaks, and you can measure the deformation and the stresses that you have. There's another one that is basically a press, and you have a big cylinder and just pressing against the other, and again you measure the bulge and then it breaks. There's a YouTube channel that they have a hydraulic press and they put everything on it, and it's actually pretty fun. As you can imagine, it's not that you can test this in a person. It's not that you can ask a person to just let's look at the deformation of your bone. It's not feasible, and unless you want to break someone's bone. I don't know. So usually these tests are measured in cadavers. So there's a limit of what samples you can have. And if you have taken your anatomy lab, it's like, well, the cadavers that you have available to do this kind of test or experimentation is limited. So these numbers that we have, there's a bias on what is the samples that we can get. Okay. Okay. So a really quick example on how to calculate the stress and the strain. So, so let's say that we have a runner, and you have a runner, and the runner has a force of 3,000 newtons that causes the tibia to shorten, and it's gonna compress by 0.5 millimeters. Okay, the tibia has areal length of 0.42 meters. And the area of the tibia is going to be this one, 3.58 times 10 to the minus 4 meters square. This 3.58 is the blue area. So you can imagine, if you imagine your bone to be hollow, the force is being applied on the blue area of your bone. Okay, so this blue area will be your 3.58 times 10 to the minus 4 meters square. Okay, so the stress is just the force divided by the area. So it will be this 3,000 newtons divided by this 0.000358. And it's going to give me a stress of 8,038,380,000 pascals of 8.38 megapascals. Okay, the strain, and you have to be careful with the strain. The strain is the ratio between the deformation and the areal size. So if the object is being compressed by 0.5 millimeters and the areal size is 0.42 meters, well, then it will be 0.0005 meters divided by 0.42, and that gives me 0.00119. Again, this is adimensional. Now, when you report strain, you will say that it has a strain of 0.12% or 0.119%. But when you are using the strain to calculate, you use the decimal value. So to calculate the Young modulus is basically stress over strain. Okay, so that will be the 8.38 megapascals divided by the 0.0019, and that gives me a Young modulus of 7.04 gigapascals, 704 times 10 to the 9 pascals. I will do more problems on Wednesday. I'll give you a homework that is going to be talking about specific about how to calculate stress and strain and all this. Okay. So here's just that. Just be careful when you're talking about strain. It's just a percentage. It doesn't have any dimensions. When you report it as a percentage. When you are doing math with it, you do the math as a decimal quantity. Okay, this is another example. We'll do a little bit more later. So this is a table of showing the strength of some materials. So the strength is that point, that maximal compressive force that they can support before it breaks. So that's the strength of the material. How long before it breaks? How much force can they support before it breaks? And I'll show you later a graph that compares spider silk with some metals. So when you hear that the spider silk has the strength of steel, what does that really mean? Like what exactly that means? And when you see these graphs of yield with the stress, it will make a little more sense. I'll make sure that I'll bring it on Wednesday. So anyway, this is the strength of different kind of bones. So you have the femur, it has a compressive strength, and you can see the range is really, really large. It's almost 100 pascals. So it goes from 131 to 224 megapascals of strength. And again, this depends on the age. It depends on the properties of the structure of the bones. It's completely different to make this kind of test on someone that has a more sedentary life, and someone that has a very active life. It's completely different if you measure the compressive strength of a bone of a 20-year-old person than someone that is 70-year-old person. So that's why you see these ranges. It's not that easy to have a specific value on the strength. For the tibia, 106 to 200 megapascals. So that's the compress before it breaks. Wood, 40 to 80 is affected by the humidity, and steel, 370. And again, it's going to change depending on the kind of steel you have. But you can give an idea of what will be the force that you need to break a bone. So you can say if you have a 300 megapascals pressure on a femur, you're probably going to break it. Okay. I used to have for the vertebra on the neck, and then students start calculating how much strength they need to break someone's neck. So I don't put it anymore. So, hey, what happened? Oh, there you go. Okay, so this is the graph that's kind of interesting. If you see, if you have a bone, and in this case, I'm talking about one of the large bones, like the femur and the tibia, one of the extremity ones, the strength that they have is different in compression, that in tension, that in shear. So bones tend to be really strong when they're being compressed, a little bit less strong when they are under tension, and really weak when they are under shear. So that's why you see a higher number of fractures on the shear than under tension or compression. When you see that multiple fractures, so when you have the bone that's being shattered, it's usually because of shear. When you have compression and tension, I'm going to go back to one of the first graphs. So you have a higher strength under compression and a less strength under tension, so you're going to break in the outside of the bone, and that's when you see the fracture, and you see like this crack fracture. We say that the bone is an anisotropic material. So anisotropic material, it means that it's going to behave different depending on which direction you apply the load. So you have the two structures of the bone. You have the trabecular area, and then you have the cortical region. So the trabecular is actually isotropic. It doesn't matter how you apply the force. It's going to behave the same. But the cortical area is actually going to matter if you have compression or tension or shear. The bone behaves different. Now, this is just another one that you may have heard about: ductile materials, brittle materials, and elastic materials. That's just the technical name to talk about materials when they have large elastic regions, or they have very short plastic regions, or they have very short elastic regions. So for example, a brittle material, like bones of an old person, we call them brittle materials because there's pretty much no plastic region. You have the elastic region that tend to be very small. You reach a threshold and then they break, they shatter. Ductile materials like many metals, like gold is a ductile material, means that they have a very small elastic region. This graph is not very good. They have a very short elastic region, and then they have a huge plastic region, meaning that it's really easy to deform those materials, and you don't require a lot of strength to give them a particular shape. And then you have elastic materials in which you need to apply, you can apply large forces that can have long deformations, and then they go back to this natural shape. Okay? But don't worry so much about this. So ideally, an elastic material behaves like a spring. And a spring, if you apply a force, it's going to be deformed, and it deforms in a linear way. And at the moment that you release the force, it goes back to its natural shape. And if you were to look at that stress-strain graph during the formation and the recovery, it looks like a straight line, always like a straight line. So that means that all the force that you apply, all the energy that you give it to the spring to deform it, at the moment that you release that spring, is going to give you back all that energy, and there's not going to be no waste of energy. Okay. In reality, most of our organs are not elastic, or they're not perfectly elastic. They are what we call viscoelastic materials. A viscoelastic material is basically one in which you apply a force to deform the material, and then the tissue is going to absorb some of that energy, and it's just going to give you back a little bit, or going to give you back a fraction of that energy. So your tendons, your bones, your muscles, all of your skin, everything is a viscoelastic material. So every time you deform it, some of that energy is going to be absorbed, and it's only going to give back a little bit. The stress or the load-unload graph is going to look like this. So you deform the material, and then when you release the force, instead of going back exactly the same way, it's going to do a different graph. And the area under the curve represents the energy that's being given back. And this blue area means the energy that's being absorbed. So in the terms of tendons, if the less of a curve you have in a tendon, the more efficient is going to be your running. And that has to do a lot with the elasticity of the tendon. So someone that tends to be high flexibility tend to be better or more efficient runners than someone that tends to be very stiff. That the tendon cannot stretch, and they can have that elasticity very well. They tend to feel that pain on the tendon, and there's this absorption of the energy, and just not that very efficient runners. Okay. There's a couple more, but that's pretty much it. Cool. Was it good? So far? Did you guys fall asleep? A little bit? Yes, a little bit. Back there, the chat, you guys fall asleep? I think they're still sleeping. Anyway, Wednesday we're going to be doing some problems involving elasticity. And then Friday we're going to start with conservation law. So that's going to be chapter 9. Okay? That's it. Have a good day, and see you on Wednesday. And Elizabeth, can you stay a little bit? Can you stay? Just 5 minutes? Yes.